Hello, this is Chuck Ridgway, Automation Technology Manager from Horner. Thanks for joining us for another Tuesday live stream. Here's our topic for today, the Cscape shift register instruction. Now really any application engineer or anyone who programs in ladder logic should really become familiar and have a solid understanding of the shift register instruction. It has a lot of different applications, and there are plenty of situations where the shift register can take what seems like a complex programming situation and turn it into a straightforward solution. Now you may be a little intimidated by the shift register instruction because you haven't used it before, or you may be very familiar with it, but you may have never used it with a Horner OCS. So whatever camp you're currently in, we're going to get you taken care of today. Now today is a video we did pre-record, but if you're watching this Tuesday at 2 o'clock, rest assured we're streaming it live and we're standing by to answer any questions you have in real time. If you're watching this on replay, give us your questions in the comment section. We'll get those answered in non-real time. All right, let's get started. Here's how we're breaking down our topic for today. We'll start with what is a shift register? How are they used in automation? What shift register instructions are included in Cscape? We'll talk about different applications where you can use shift registers. And of course, we're going to give you plenty of demonstrations throughout the program today. All right, here we go. What is a shift register? Well, a shift register is a register or a series of registers that is designed to allow its contents to be shifted left or right. And functionally, shift registers serve as either data storage spaces or data movement devices. As a data storage space, shift registers are valuable in applications such as data logging and mathematical operations. As a data movement device, shift registers are valuable in applications where you're having sequential operations that you need to track. Now, in terms of how shift registers are used specifically in automation, let's talk first about the use of shift registers when they're being used as a data movement instruction. So you could have an application where you need to track product as it works its way through a machine or a process. You may have an application where you are sorting dissimilar products that share the same material handling equipment. So you have different types of products moving through the same equipment, and you need to be able to sort that out. Shift register can be a valuable tool for that. Now, when we're using shift registers as data storage instructions, here's a couple of examples of how you might use a shift register. First of all, how about for high-speed data logging? Maybe you want to capture and log process data extremely quickly, say every single scan, for a short burst of activity so you can analyze that data later. Another case, maybe you need to capture historic data in some sort of form where you can periodically examine the data and manipulate the data using other instructions and logic. But in terms of gathering the data, the shift register is a valuable tool to store that data away initially. So just a couple examples of how they can be used in automation. What shift register instructions are available in Cscape? Well, let's start with Bitwise Instructions. Over there to the right, I'm showing you the Cscape project toolbox, which is where you can find the different categories and all the different instructions when you're programming either in ladder logic or in variable-based ladder logic. And under Bitwise operations, we have 4 instructions that fit under today's topic. Those are shift left, shift right, rotate left, and rotate right. We'll cover those in great detail here in a moment. Also, if you take a look under move operations, you'll see we have element shift and element rotate. Those are also perfectly applicable to today's topic. Let's start with those Bitwise operations, the Bitwise instructions, starting with a shift left. What does that instruction do? Well, that instruction operates on either a word or dword variable, and it operates upon the bits within that word or dword. Now, from an input standpoint to that function, The first input is the variable that contains the string of bits that need to be shifted around. So that would be the word variable or dword variable that contains, again, the string of bits that we're going to shift to the left. N is the number of positions that we're going to shift those bits. Usually that's 1, but it could be something other than 1, but usually not. Output. What is the output of the shift left? Well, it is the result of doing the shift. What is the bit pattern after we do the shift? Well, that bit pattern after the shift is copied into the output. Now, when we're shifting things to the left, what happens to the rightmost position, which started out with a value and then had its value shifted out? Well, a 0 is moved into the rightmost position when we're talking about a shift left. Another question you may have is, does the shift left instruction pass power or not? Well, it does if the bit that was shifted out of the leftmost position was a 1. If the bit shifted out of the leftmost position was a 0, then it doesn't pass power. Okay, next we're going to show you graphically what's happening here. So at the top, I'm showing you the bit pattern for the input variable. And then we're going to be shifting that input variable to the left, or at least the bit pattern. We're going to be shifting in a 0 into the rightmost position. And we're going to be shifting a value out of the leftmost position. At the bottom there is the output variable. So that's what the bit pattern looks like after we perform the shift. So you can see that our rightmost position contains that 0 now that was shifted in. And because we shifted out a 0 from the leftmost position as a function of the shift, we are not going to pass power flow to indicate that a 0 was shifted out. Okay, so graphically that's what's going on. Next, let's take a look at a shift right. I think you can imagine that it's identical to the shift left. We just shift the bit pattern the other direction. We still have an input variable, which is the variable containing the bits to be manipulated. We have an N input, which tells us how many positions we're going to move. This time, when we move a 0 into the bit pattern, we're moving it into the leftmost position, and we're shifting out the bit that was in the rightmost position. Same rules for power flow. Let's take a look at the diagram here. The diagram shows just what you would expect. Okay, we're shifting everything in the input variable to the right. We're shifting in a 0 all the way to the left. We're shifting out the rightmost position. In this specific bit pattern I'm showing here, the output variable is shown at the bottom, and because we shifted out a 1 with this specific example, we are going to pass power flow in this case. Now, other than the shift left and the shift right, we also have rotate instructions where we can rotate left or rotate right. These are very, very similar to the shift instructions. The only difference is that you don't have a 0 that you're shifting in, and you don't have a bit that you're shifting out. It's completely self-contained. Let's take a look at the bit pattern next. What happens is, in the case of a rotate left instruction, everything gets moved to the left, and then the leftmost bit gets rotated all the way around to the rightmost position. So there you can see the input variable at the top, and then at the bottom you can see the result after we shift everything to the left, including that leftmost position then rotating all the way back around to the right. So there's no loss of data here. And from a power flow standpoint, a rotate instruction always passes power flow. So some of you who are experienced programmers may be saying, now wait a minute, I've used shift registers before from other PLCs, and these don't exactly look like shift registers. They're very close, very similar, but not exactly the same. So you'd be right in that there's a couple limitations with these bitwise operators that we've been talking about. What are those limitations? Well, yes, they're full shift registers, but they only operate on full word or dword variables. You can't manipulate a portion of those variables, okay? So that's a limitation. Also, you can't shift in a value like a traditional shift register. You know, you're shifting in a 0 in the case of the shift left and the shift right. You're not shifting in a variable, for instance. And so what's that all about? Well, basically what it means is with the OCS, you have a couple of additional instructions we're going to talk about that probably have the characteristics that a lot of you are used to with your other PLCs. And those would be the element shift, which we often call the multi-shift function. Okay, let's dive into this element shift, because this truly is the most useful instruction when it comes to shift registers that is available. So let's talk about the element shift, sometimes called a multi-shift. First of all, instead of just operating on a word or D-word variable, it can operate on bit type variables, byte type variables, word type variables, and D-word type variables. Okay, all of those can be operated upon. Very versatile. Now, because of the fact that our multi-shift instruction doesn't have a separate instruction for left and right, you're going to see more parameters that need to be filled in for the function block. But don't let that intimidate you. It's very straightforward. The source for the multi-shift instruction is the location of the data that's going to be shifted. And typically, that is going to be a variable that is an array. So a variable-based array, typically, okay, of the appropriate type. If you've got a shift register of bits, then it's going to be a variable-based array of bits. If you are shifting around words, it's a variable-based array of words. So the source is the location of the data to be shifted, most typically a variable-based array. Okay, length, the number of elements in your total shift register. So if you have 100 words in your shift register, then more than likely your source is going to be a word type variable array, probably length 100, and then the length that you fill in is just going to be a constant of 100 probably. Okay? Number, once again, is the number of positions we're going to shift, usually 1 but not always. Direction is a variable. If you want to shift left, put an always on or a variable with a value of 1 in that field. If you want to shift right, put an always off or a variable with a value of 0 in that field. Input, that is going to be the variable that will be shifted in to the first position, okay? And the output is a variable that is where the data that is shifted out is going to be copied into. So any data that gets shifted out using the multi-shift instruction goes into the output variable. Sometimes that is the key variable that you're looking for. Other times it's just an afterthought. So we'll go through a couple of examples there. Let's take a look at what an element shift instruction could look like when I've configured it as you see here. So what you've got there in the top center is we have a very simple shift register that's based on word type data, and the source is a variable based array called weight with a dimension of 4. Okay, so I've shown graphically on the screen weight 0, 1, 2, and 3 from right to left. Again, the length is 4. I'm going to shift 1 position. I've got always on in the direction field, which means I'm shifting left. My input is the data I'm going to be shifting in. I'm showing it there on the upper right hand side. My output is the variable that I'm going to shift my data into, that is falling off the end of the shift register. Okay? And then my result you see there at the bottom. So you can tell everything's shifted over from right to left. The leftmost position, or weight sub 3, was copied to the output variable, and the input variable was copied into the rightmost position of weight sub 0. Okay, so that is an element shift instruction. Details when we're shifting left. Now let's take a look at what happens when we shift right. A little bit different. Notice that I've drawn the input variable and the output variable now on opposite sides here. Because when we shift to the right, basically with the same configuration we had in the previous slide, you can see some differences here, okay? Basically, the input variable is now copied to the last position, or the leftmost position in the shift register, and the value that fell off, which happened to be the rightmost element, it got copied to the output register. Okay, so there at the bottom you can see what things look like after the shift. So that was the multi-shift or element shift function, by far, in my opinion, the most useful. Let's not forget rotate though. That can be useful sometimes as well, all right? It's almost identical to the multi-shift function. The only difference is, as you would expect, it does not have an input variable or an output variable because it is completely self-contained, okay? No data falls off, no data gets shifted in. Just like the multi-shift, you have a source, a length, a number in terms of how many positions you're going to shift, and then also a direction variable that allows you with the same function block to either shift left or shift right. Here's what that element rotate instruction looks like graphically. Again, I think it's just as you would expect. If we are rotating left in this case, then you can see everything moves from right to left, and the leftmost element of weight 3 gets copied back down around again to weight 0 because of that action. Now let's talk about some applications that you might run into, or at least some more real-world applications that will get your, I guess, your juices flowing in terms of thinking in how you can use the shift register instruction in a future application. So here we have an application. It's a conveyor application, all right? So we've got a motor that's controlling a conveyor, and there's also an encoder connected to the motor as well. So every time that encoder does one revolution, so the motor does one revolution, the encoder does one revolution, every time that encoder does one revolution, a marker tick turns on, okay? A marker signal turns on. And it turns out the linear distance that the conveyor belt travels with every revolution of the conveyor is 1 inch. And in our application, we are detecting when packages are present on the conveyor, and approximately 192 inches later, we need to turn on a zapper to zap any packages that are present. But we don't want that zapper on when there are no packages present. So that's what we're trying to accomplish in this particular application, and we're going to use a shift register to do that. All right, we're going to use a bit type or Boolean type shift register. Now, what is going to be the contents of the shift register? Well, the shift register contents are going to represent the marker ticks that exist from the package sensor to the start of the zapper. And we mentioned in the previous slide there are 192 of those marker ticks. So our shift register size is 192 bits, where each bit represents a marker tick. Now, we're going to shift it to the left, and then what are we going to shift in to the shift register? Well, it's going to be a package sensor value, 1 or 0, okay? So if a package is present when a marker tick comes around, okay, and a shift is performed, then we're going to shift a 1 in. If around on the next tick of the conveyor, so 1 inch later, that package is still present, we're going to put another 1 in. Okay, so we're not just detecting the leading edge of the package, we're going to detect the entire time that that package is present, and we're going to pass a series of 1s onto the shift register, so at the very other end of the shift register, when those bits fall off the end to the output variable, if those are a 1, then those 1s are going to turn on our zapper relay. And if those are 0s that fall off the other end, then our zapper relay will be de-energized. Okay, so that's basically what we're doing here with our shift register setup. And here's how we're configuring the shift register instruction specifically in this case. So now let's go ahead and fire up Cscape and take a look at what's happening with our program here. So I have configured Cscape for this application I just described, and really the operation to do all the shifting and everything is going to be performed in just a couple of rungs, so pretty straightforward. So the input to a shift register, basically whenever that input is on, the shift register is going to perform a shift. So it's actually going to shift as it's been specified. Now, in this particular case, we only want to shift once every time we get a marker tick with every revolution of the encoder. okay, which tells us we've traveled an inch. So we don't want the conveyor marker signal from that encoder to go directly into the shift register. Otherwise, if it's on for more than one logic scan in a row, we're going to do multiple shifts when we only want to do one. So what we're doing here is we're creating a one-shot based on the conveyor marker to ensure that every time that marker turns on, we get one and exactly one shift into the shift register. Okay? Now let's take a look at how we configured that shift register. We have a variable-based array called marker ticks, and I'm going to go ahead and go to my tag browser so you can see that here. And you'll see that it is a variable-based array with 192 elements in it, from 0 to 191. Okay, and we're going to reference marker ticks 0, the first element, as the start of the source of our shift register. The length is 192 bits because we've selected bit type here. We're going to shift one position. We're going to shift to the left, so we put always on here instead of always off. The input to the shift register is the package present sensor. The output from the shift register 192 bits later is our zapper relay. Again, so if we shift out a 1, our relay turns on. If we shift out a 0, our relay is off. Okay, so that's the setup, everything we have here for this application I've talked about. Let's take a look at a very similar application running on a demo here. Okay, so what we have here is a reduced version of the application we talked about. In the application we talked about, we had 192 ticks, or 192 elements in our shift register that represented the distance in ticks between the package sensor and the zapper equipment. To show this on the screen as a demonstration, I knocked that from 192 elements or 192 bits down to 16. Okay, but it still works the same way. So what we have here is we have a conveyor that's sitting there running. I didn't put a run stop indication, I probably should have, but there's no conveyors on it right now. So I'm going to go ahead and simulate adding a package to the conveyor. And you can see I have 3 consecutive ones go by. That means that package is 3 inches long if we have 1 inch per tick. And as that package moves its way down the conveyor, those ones are moving their way to the output, and they're turning the zapper on, and then when they're done, they're turning the zapper off. Okay, I'll go ahead and start another package here, a little bit narrower one, and let's start another one that's a little bit wider. And as you can see, I've got ones that are shifting down with every tick of the encoder as that conveyor runs here. Okay? And at the appropriate time, I'm turning on my zapper, and it comes on and stays on for the duration of the package. Okay, so that is what we are demonstrating here with this first application of basically keeping track of the position of a package as it moves through a piece of material handling equipment. Let's head back to our material, and next let's talk about another potential application for a shift register, and that is a level sensor type application where we want to average a series of analog readings to get a better reading to work with from a control standpoint. So let's say we have a sensor that's monitoring the water level in a tank, and because of turbulence or waves or whatever the case may be, we have determined that if we take the average of the last 10 analog readings, we're going to get a result we're happy with in order to do our monitoring and control. So we have effectively a need to create a shift register with the last 10 analog input values from our sensor. So in this case, because we are doing some math and we're doing some averaging, we're going to go ahead and set up our shift register to use real type variables. That way we can use math and not lose any resolution or anything. When we set up our shift register instruction, the source is going to be that array of analog readings with a length of 10 because we want to look at the last 10 readings. We're going to shift one analog reading in at a time, and it's going to be shifted in from the current analog reading, and we get a new current analog reading every single scan. All right, we're going to shift it to the left, which means we're shifting it from lower numbered member of our variable array to the higher numbered member. And then in this case, the output that falls off the end of the array isn't all that important. We're only worried about the last 10 values, and that output variable is going to contain the 11th value. So we're going to ignore that one. Okay, it's not really important. We still have to configure it, but it's not something we're going to be concerned with, doing anything with in our program. Okay, here's how we're setting up that multi-shift instruction in this example. Again, floating point is what we're using. Our source is an arrayed variable of 10 real values, which represent the real value of the last 10 analog readings. We're shifting in our latest analog reading every scan. Okay, and again, at some point or at every scan basically, we're going to be looking at all 10 of those values and creating an average using some math. Okay, so let's take a look at that. Back to Cscape. What I can do here is I'm going to go from my zapper section of my program to my analog averaging section. Here's what I'm doing. I pretty much did everything in a couple rungs again. All right, so what's happening here? Well, unlike my last example, I actually do get new analog readings every scan to shift into my shift register. So I don't need to worry about using a one-shot to shift the shift register. It's okay to shift in a new value every scan because I have a new value to shift in. So I can use always on here. Now, as all of you probably know, or a lot of you at least, the analog values come in as integers to the OCS, and if we're going to create a shift register full of real values that we can use in calculations later, then we're going to need to convert that analog value, the current reading, over to a real value before we shift it in. So let's take a look at our shift register configuration here. Okay, our source is a variable-based array called readings with 10 members, and we can see that as we look here under readings. Readings sub 0 through reading sub 9. So we're going to always reference the first member of the array if that's where our shift register starts. It is 10 D words long. Now keep in mind, D word just refers to the length of the data, not to the type. Okay, so double words or 32 bits is appropriate for a floating point value. Okay, we're going to shift one at a time. Once again, we're going to shift left. The value we shift in is going to be this real value of our analog sensor reading, and then the output value that we shift, that gets shifted out, is the oldest reading or the 11th reading, and we're not going to use that anywhere else in our program because we really don't care about it, but we're going to go ahead and configure it because we have to. So that's our shift register configuration. Next, in terms of our calculation of our running average, first of all, we're delaying the first second that the controller is running. So the first second after power up, we don't have 10 good readings yet from our analog sensor, so we're going to wait a full second. And during that second, we'll probably read a couple hundred analog readings. So after a second is done with, everything is stabilized, and now we've got a shift register full of 10 values, and then I've got this math expression, which all it's doing is basically totalizing all 10 of the readings that are in the shift register, okay, that are currently in the shift register, because next scan it'll be 10 different values, right? Or at least one value will have changed as of next scan. Okay, and then now that I have the total of all these values, I can divide it by 10 to get my average that I can use for my control elsewhere. Okay, so that's really all that was required for the setup in this case. Back to our real-world OCS. Let's take a look at our water level demo. So on this screen, what I've got is I'm showing all 10 elements of the shift register. Remember, we had 10 consecutive floating point values. Those floating point values were really just conversions of the 0 to 32,000 analog values coming directly from the analog input. Okay, so here is, of course, the 10 individual elements, and then every scan, we're shifting in a new value from the analog input converted to real. Every scan, we are recalculating our average from the last 10 conversions, and then I've got a engineering unit conversion there from counts over to feet. I'm going to go ahead and manipulate this particular analog input on my handy dandy simulator to show the water level going down, obviously very quickly. But as you can see, we have pretty stable engineering readings, even though we do have some bounce in the individual conversions into the analog card. So hopefully that gives you another way in which you can use shift registers to store away data that you can then use for some sort of calculation. In this case, just a simple average. Okay, so that wraps up the material I wanted to present to you today. So hopefully those two examples of how to use shift registers and different ways you can use shift registers have got your juices flowing so you can think about how you're going to use that instruction in the future. Now next week we have a topic which is using OCS in a 12-volt DC environment. And this was by request from one of our viewers who basically was interested in learning what are the implications of using an OCS in a 12-volt environment, which is not your normal 24 volts DC. You typically would find this maybe in a mobile type application or a battery powered application, for instance. So remember, you can always request topics and we'll do our best to deliver those for you. So we're here every Tuesday at 2 o'clock. If we pre-record like we did this week, we'll still stream it live and answer questions live. And you've always got the option of asking questions in the comment section anytime you are watching a video on replay. One last reminder before we sign off, and that is if you haven't subscribed to our channel yet, don't hesitate. It doesn't cost anything. And if you choose notifications, you'll be notified every time we go live or every time we post a new video. Okay, until next week, everybody stay safe.